I'm going to talk to you this afternoon, as you can see here, about technologies for desalination wastewater treatment in Israel, but in fact it's going to be a sort of, I would say, a melange between topics in which I'll describe what we are doing in Israel, including some descriptions on treatment, on technologies for water treatment and wastewater treatment. Okay, since as I understand, this is a kind of an issue that you people are not that familiar with, and there's a lot of interest in Chile, especially because of the water drought that Chile is suffering today, especially this, the central and the northern part regions in Chile. It is very, this is a very important issue, so that's why I would like also to introduce some of the ongoing technologies today in the world, and as well as in Israel, that for water treatment and wastewater treatment. Let me first, just one comment. If you have any question, don't wait for the last minute, okay? Just raise your hand and I'll be glad to answer while I'm talking, okay? Good? Because I would like to have it as a sort of a discussion in between, right? Okay, so don't be shy. Let me start with this nice satellite view on the region of Israel, and I don't know how many of you are familiar with it, but you probably heard some names of places. For instance, this is the Lake of Galilee. Okay. Yes, which is in the northern part of Israel. Here, what you see here, this is the border, okay, between Egypt and Israel. Here is the border between Israel and Jordan, okay, and here more or less starts the border between Israel and Syria, and on the northernmost part of Israel, this is Lebanon, right? And of course, this is the Mediterranean Sea. Okay, Jerusalem is here, and in fact, the place where we are staying, our laboratories are there, is a place in the middle of the Israeli desert. From here, more or less, from this line southward, okay, the Israeli desert starts. Okay, actually, it forms the most of the part of the area of Israel, almost I would say 65% of the area of Israel is a desert, okay? And I live in this city which is called Beersheba. It's a very ancient city. It is mentioned several times in the Bible, okay? As a city of our ancestors. And our main campus of the university which I belong to is here in this city, and we have our laboratories, as I said, as a branch of the university here, and it's situated in the desert because we are dealing there in this place mostly with desert-related issues. Okay, it's water, it's agriculture, it's physics, it's chemistry. All of these topics are focused on desert issues, right? That is why it is there. Now let me get back. I'll show this biograph later on, but let me get back to the. No, I'm sorry, I'm in the wrong direction. Okay, to the first slide. Okay, I want to start with a short summary on the current situation of water in our country, in Israel. And the reason is that water issues as well are very important in Israel as well as in many other countries around the world, including Chile, of course. we cannot live without water. The point is that due to climate changes, we suffer very much from many years that are almost totally dry. We don't get any precipitation. And but the status today of the state of Israel is that we have almost actually more than 680 million cubic meters per year. We are getting water from huge desalination plants, okay, that we have along the Mediterranean coast that I showed you before, and this forms more than 60% of our annual water consumption. Okay, so you may think that we have plenty of water, but this is not the situation. That is what our government always tells us. Don't be too happy with this, even though we are sure that we'll have constant supply of water. It doesn't mean that you can waste water. You still have to save it, okay? Because water is a very precious, very precious commodity that you have to keep and not to waste. The other point is that more than 80% of our wastewater is recycled, okay? And most of the recycled wastewater is going for agriculture. We recycle the wastewater. This is municipal wastewater as well as industrial wastewater, okay? I'll talk about it later on in a little bit more details. And we use the water for what we call this kind of water, the recycled water, for what we call unlimited irrigation, which means that you can irrigate even those crops that are edible, okay, like potatoes, tomatoes, cucumbers, okay, that contain actually a lot of water, and you can use them safely even though they are irrigated with recycled wastewater. In general, our groundwater is well preserved and in good quality, and that is because our government and also the citizens are it is very important to keep the quality of water, to maintain the quality of water on a high level constant high level, and which means that we shouldn't pump out water more than we are allowed to do it in such a way that, for instance, water from the Mediterranean Sea will not intrude into our aquifer and make them more salty and introduce more salt or even more contaminants than it should be. So they are very well preserved. We are also harvesting during the winter when we have precipitations water. It's not enough yet. As you can see, it is just 3.5% of our water consumption. The fact is that most of this water, the flood water, goes to the Mediterranean Sea. We look actually, okay, but a larger part of it we manage to harvest. We have, as I mentioned already, we have a very intensive and efficient agriculture, okay, which means when I'm saying very efficient and intensive, I mean that during the years we managed by a very nice scientific activity, okay, we managed to understand how to control the water well in order to get a high efficiency of crops going on, okay, and giving us the agricultural product that we need. So water consumption today in agriculture is very, very efficient, okay? And maybe I have a graph that will show you the water consumption in agriculture during the year, and you will see that it declined during the years because of this scientific activity and the know-how that was developed in regard to this. Industries use less and less water, okay? Again, because they are very well aware to the situation that we have to save water, and we are not. We have to face the truth. Okay, the fact that the industries are using today less and less water is because they are getting charged a lot for the water that they are using, that they consume. Okay, that is why they reduce the amount of water that they consume today. Otherwise, I guess that they wouldn't mind, wasting water as they did in the past. This is a very important point. The public awareness for water saving is very much developed in Israel, and if I'll have time, I'll show you at the end. I guess I have two very short videos that will show you the what we have in our TV in our media, TV and radio, in order to convince the public that we really have to save water, and this is a very, very important point. As you may know, Israel is leading in the water industry. Okay, we have today more than 300 companies dealing with different issues that are related to water, and in a couple of slides I could show you an example of one of the big companies that we have in Israel that is really heavily involved here in Chile in different water issues. Okay, so the driving force for all these kind of activities that we have in Israel, and it should be also the driving force everywhere in the world that suffers from lack of water, is first of all, we all understand that water is essential for life, and when we have water scarcity and water crisis, we should take actions, okay? And all these achievements that we have now in Israel are thanks to the fact that we really took different actions. Actually, the first action that the Israeli government took was not as you see here, 1959. And I'm not going to read all of this, but this was the water law, which states that water is a public property, okay? Which means nobody is allowed to use water without getting, first of all, permission from the government. Okay, we have special authorities. We have the water authority for this. We have a company that, just one company which is owned by the government. It's a public company that distributes water throughout the country. Okay, and this is the only company that is allowed to do it. You are not allowed to dig wells in your backyard. Okay, as it is unfortunately the situation in many different countries, and I understand that even in Chile people are doing it, and it's very important because this is probably one of the main ways by which you really can control the consumption of water, the use of water, okay, and to keep your water sources. The Ministry of National Infrastructure and Water and Energy, and as well as the Water Authority that is part of this ministry, they are in charge of the entire scale of water issues that we have in Israel. Actually, the first, I should say, technological act that was taken in Israel in order to supply water to every house in our country was this. This is the Israeli National Water Carrier, and the aim was, you remember Lake Galilee? This was at that time our main water reservoir. It's a lake, okay, a natural lake, of course. And the aim was to bring water from there, to pump water from there, which is around 450 meters below the sea level, okay, which just shows you that we have to apply a lot of energy, you know, the pumping energy, hydraulic energy, in order to bring the water up to this level, and then to supply to this pipeline, okay, to all the parts of Israel. So this was actually the main water supply in Israel until we started the desalination era in our country. Today, the situation is that we don't pump almost any water from Lake Galilee, okay? Because what happens during the years, you know, if you overpump, okay, from natural lakes that you have or any other lake that you have in your country, sooner or later it will become deteriorated, and that's exactly what happened to Lake Galilee. Okay, and remember, this is the only lake that we have in Israel, not like in Chile that you have so many lakes. Okay, but thanks to the desalination activities that we have today in Israel, and the fact that we could afford stopping almost totally the pumping of water from Lake Galilee, it recovers now. It takes time, but I believe that it will recover, fully recover during the years. Now, what happened that the Israeli government decided to go heavily into desalination? You see here, this one. This is the this graph shows the average rain quantity, precipitation quantity in terms of millimeters that we got in Israel as a function of the year, and you see it starts from 1920 up to 2020 almost. Okay, here, this year was a terrible year, after which you see, it was the precipitation that we got here was less than 50% of the average, the annual average that we get. Okay, and after this year, you see it here. Okay, here, this is the one, and that was not the only one. Okay, it followed several years that came before that were also very poor in precipitation, and this is, by the way, what happened, okay, to Lake Galilee. When you overpump, okay, suddenly you can see different islands that are growing in the middle of the lake, okay. Following this disaster that we have that year, 1999, there was a parliamentary committee that was established by our parliament. Okay, I'm not going to talk on all the conclusions, but the main conclusion was that Israel has to go very fast into desalination. Okay, we have the Mediterranean Sea. The water there is, we have plenty of water there, okay? I wouldn't say endless, okay? But plenty of water there, and we can use it as a huge and the main source for our water for the coming years. So that's exactly what was done, and now I promised you that I'll show you this, this slide again. And now, today, we have 5 very large desalination plants along the Mediterranean coast. Okay, actually, of them are considered the largest in the world in terms of their capacity, the annual capacity. Okay, the annual water capacity that we get from them. And also the most modern, most advanced in the world. And these are the 5 that we have, okay, that are marked here. There's the 6th one probably will be in the northern part of Israel. But these are not the only desalination plants that we have. We also use brackish water. Okay, do you know what is brackish water? You know, we all know what is seawater. Okay, brackish water is water that comes from underground. Okay, and it contains different or a variety of salt concentration. Okay, and because of this we cannot use them as is. We have to remove the salt out of the water in order to be able to consume it. Okay, seawater contains the Mediterranean seawater contains 5 grams per liter of salt. Okay, and by all means it is salty. You cannot drink it. Okay, the Pacific has, I guess, almost the same. It maybe a little bit more. I don't. How much is it?
30.
30? Ah, okay. So less than that. Right. Okay. Even this is you cannot consume it. Okay, you cannot. Brackish water can contain salt starting from, I would say, 1,000 ppm, 1 gram per liter, okay, up to 15 gram per liter, okay. You cannot consume this kind of water. You have to remove, as I said, the water from the salt from the water. So in different places, especially in the desert part of Israel, we have a small and local desalination plants that desalinate brackish water, okay, for the local consumption of the different settlements that we have, especially along this valley. This we call the Arava Valley. There are quite a few settlements along this valley, and the city of Eilat, which is the southernmost city of Israel. It is not. You cannot see it here, even though it is marked here. Okay, the largest British water desalination plant is located here, not far from the border between Israel and Egypt. Okay, so this is the water activity, the water desalination activity that we have in Israel. I think that I'll skip most of the coming slides just to show you. I don't have to convince you that in Chile, okay, first of all, you see, this is, I managed to find it just a few days ago. This is the annual precipitation in Concepcion, okay, and you see, actually, it is very significant, the decline in the precipitation that you get there, okay? More than 30%. It's a lot. It's a lot, okay? And that's what happened with the temperature, okay? Some people claim that they are interconnected. I'm not that convinced, but we are not going, this is not the topic of this, this is not the topic of this lecture. Okay, so I'll skip this. You have many problems. Avocado. Yeah.
Maybe not all of our students are aware of the water issues. So maybe you could, I mean, not maybe in detail, but maybe you could, maybe the previous slide that you showed about arsenic and Antofagasta, maybe that might be something interesting for.
Okay. Right. Okay. I'm glad because I stayed in Antofagasta altogether for 3 months. Okay, it was the first time it was 2 months, and the second time 1 month. I was in the NCU. I'm sorry, UCN. Yeah, I'm always mixed. You're using so many abbreviations, you know. Yeah. So there, I learned a lot about the fact that one of I should say, the sources of water that comes to Antofagasta, okay, contains arsenic. In fact, today the situation is much better than it was in this time, okay, between 1958 and 70, okay. This source is located 200 kilometers to Antofagasta. Maria, what is the river and the name of the river? I don't remember. No, okay. And they have this is one of the main sources, okay, of the water in Antofagasta. And imagine during this time, this kind of water was supplied. You know, almost 1,000 ppm of arsenic in water. Okay, I'm saying it because the highest limit of arsenic that is allowed for our consumption is less than 50 ppb, 50 parts per billion. Okay, which is six, almost six orders of magnitude less. Okay, arsenic is very toxic. It causes many different problems, health problems, including cancer. You know, I'm staying quite a lot in India, and in India they have the same problem where people are drinking water high arsenic content, and that's because they do not have any other source of water there. Okay, and I saw many photographs, terrible, believe me. Anyhow, today they have since actually not today, since 1970. Okay, this plant in Salar del Carmen was established. I visited there the last time that I was in Antofagasta, and there, in this plant, they remove the arsenic down to a very safe level. Okay, so today the situation, the status of the water in Antofagasta is quite good. Okay. So I don't know. I can talk on this issue for an hour, you know. And okay, so I'll go on. If you have any questions, please. Okay, right?
Thank you, Yoram.
Okay. Yes. Was it okay?
Sorry, why does St. George get so tight from 57 to 58?
I guess that's a good question. I guess that is because at that time, I'm sorry, at that time they started to use the water that comes from this river. Okay, but this is my guess. Okay, I noticed there, and I don't have any answer for the fact that here the level of arsenic is rather low, and here just of a sudden came. It is not just of a sudden. You have to take into account that these are almost 30 years. Okay, no, I'm sorry, almost 12 years. Okay, right? So maybe this is the reason for that. Okay, but for sure the reason for this kind of this very low level is because of the treatment that they apply now to the water, right? Okay. Right. So I promised you I'll just go briefly over it. We have in Israel this company, ID Israel Water Desalination Enterprises. Okay, it's a very large company, and you can see just what is the how intensive is the activity that they have here in Chile. In Chile, starting in 1991. Okay, and today they are building, or they they will start building, actually, this has to be updated. They will start building a new desalination plant, a rather large one. Actually, this is the largest one that you have, that they built so far in Chile, in this place, for the, for...
What unit is that? Is it meters per second, meters per hour?
Oh, that's a good question. These are cubic meters per day. Okay, right, I forgot to put it. Good question. Okay, cubic meters per day, right? Okay, so this is in the north, as you know, for one of the mining companies, and this is a very big challenge because they have actually the desalination by itself on the coast is today it's not a technological challenge because we know a lot about it. Okay, the real challenge here in Chile is that from the coast, once you have the desalinated water, you have to pump it to almost 3,000 high, almost, yeah, and around 200 kilometers. Okay, this is the real challenge here. Okay, both technological and cost-wise, because it costs a lot of money to transfer the water to these distances and these elevations, right? Okay, I'll skip this. This is a okay. I think that I'm going to. By the way, what is the time that I'm having?
We have the classroom up until 1:15, so we're okay.
Okay, but let me make it short. I could give you a lot of examples, but I'll skip it. Okay, now let's talk. Yeah, no. All over the world there are so many. Unfortunately, so many examples that you face the problem of water shortage. Okay, so let's talk a little bit about water technologies. Okay. This is a list, I should say, of all the water technologies that we know about today. It doesn't go to say that all of them are being applied. Okay, in fact, just a few of them are today are applied for massive water desalination, for instance. Okay, some of them are applied for other types of water treatments. As you may know, desalination actually started by simple or not simple distillation. Okay, you are all, yes, you are new, okay? Or not yet, but we are studying chemical engineering and we all know distillation, okay? Distillation is almost the immediate technology we would like to think about to separate between water and okay, and indeed this was done since many years ago. Okay, and all these here under the thermal. Okay, all these technologies that are listed here are actually thermal technologies by which we distillate water, and these were applied mainly by those countries that, first of all, don't have water sources, but instead oil. Okay, so since you cannot drink oil, okay, at least you can mix water with the oil. Okay, so they burned oil, distillate the water, and have desalinated water. And I mean those countries in the Persian Gulf, Saudi Arabia, okay, all these kind of countries. They actually started with the massive desalination plants, thermal, okay? But today, please take a look on this part of the map, okay? Today, we have the membrane technology, and the most modern technology for water desalination is reverse osmosis today. Okay, you probably, I guess you heard about it. Did you? Did you hear about reverse osmosis? Okay. So reverse osmosis today is the leading technology for desalination of water, and you can see it here. Okay, this is an up-to-date map. Okay, it was taken from this article, which was published this year. Okay, and you can see that reverse osmosis (RO) okay holds 60, almost 70% of the total capacity of desalinated water today in the world. Okay, the second one is MSF, multi-stage. What is F? Multi-stage flash? Yeah, probably. No, this is MSF, yeah, multi-stage flash, yeah. I'm not that familiar with thermal desalination, but I understand that this is this is a very high, very efficient way to distillate water by thermal methods. Okay, and the other one, which is also thermal, this is MED, multi-effect distillation. We have also electrodialysis. Okay, you can see it here in the green. Okay, if I'll have time, I'll show you one slide or two about it. But this is another technology by which we apply actually electric fields in order to remove salt from water. Okay? So again, reverse osmosis today is the leading technology. And this graph shows you the different types of water that today we are using in order to desalinate and to supply to the public. Okay, so as you can imagine, the larger part of this kind of water comes from the sea. Okay, and this is seawater, as it says here, SW. SW we use for seawater. The other, I have errors, I forgot them. Okay, this is seawater, and this is wastewater. Okay, wastewater becomes today a very, very important water source all over the world. Okay, and the reason is multiple. Okay, actually, there are two reasons for that. Okay, first of all, to save water. Secondly, to save the environment. Right? Because when we take water out of waste, we are left, and we do it efficiently, we are left either with a concentrate or with a dry waste, okay? Which is much easier to deal with than with huge amounts of solutions, if you wish, okay? So brackish wastewater becomes a very important water source today. The other part is river water, okay, and no, sorry, okay, I'm sorry, I mixed it up. Actually, this one was for brackish water, okay, the arrow somehow moved a little bit. This one was for brackish water, and this is for wastewater, okay, this one. But again, I want to emphasize it. Again, still the water, a very important water source. Okay? Right. Okay, I'll skip all these. This is actually very important. I don't have to look at the entire details, but this is I'm showing it because it's a very important number. The fact is that when we desalinate water, we are always left with what we call brine, with concentrates. Okay, because you cannot, for different reasons, okay, you cannot take the water completely out of the salt water. Okay, either whether it is brackish water, whether it's or seawater. Okay, you cannot take it. So you are left with a concentrate, or as we call it, brine. Okay, and we are this number actually here, the 40% shows you the ratio between the water that is pumped into the desalination plants and the water that we get as a product. Okay, it is in fact not that important when you are dealing with desalination of seawater. Why? Because we can pump back the brackish water that we get, or the concentrate, back to the sea. Okay, but it is a real problem if you deal with inland sources like brackish water, like wastewater. Okay, because then when we get the concentrate, or we get the dry material, we have to we cannot drop it everywhere. Okay, we have to deal with it cleverly, so to protect the environment. So it is very, very important to, in these cases, that the recovery ratio will be as high as possible. So this number is an average recovery ratio of the entire desalination activity that we have in the world, okay, which is rather low, as you can see. Okay, so this is one number that we would like to improve. Now, about cost. Okay, why reverse osmosis becomes the leading technology today? This is the reason. You can see this is the cost per 1 cubic meter in terms of dollars, American dollars, for 1 cubic meter, for the production of 1 cubic meter of the desalinated water. Okay, this is the cost, what we call X factory, at the end of the line of the production line. Okay, before selling it to the public. And you see that the reverse osmosis is in a very good situation, okay, with respect to the thermal technologies and many other technologies. So this is the main reason why this reverse osmosis today is the leading technology. I'll skip this. I'll skip. This is also this comes to show you that again, this is the amount, the cost of desalination per cubic meter per day in different places around the world. Using reverse osmosis technology, okay, and you can see here in these are for different locations in Israel along the Mediterranean coast, and you can see here that again we manage in Israel to produce this kind of water in a rather low price. Okay. Right. Okay. Okay, I don't know if you are familiar with this scheme, but it shows you in general the different degrees of filtration. Okay, you have here, again, I'll go very fast on it. You have here very large particles that are being, that you can separate them just by precipitation, sedimentation, and so on and so forth. Here, we need, for this size of particles, okay, here you have the scale of the particles, we need microfiltration, then ultrafiltration, then nanofiltration, And then at the end of the line we have the reverse osmosis. The reverse osmosis is actually the most, I would say, fine filtration technology that we have. Actually, this is not filtration what we are doing here. Unfortunately, I don't have enough time to go into the mechanisms by which we can separate water from salt in reverse osmosis, but there is still a very large dispute between the scientists on the different technologies, different mechanisms by which it can be done. But the fact is that it is done. Okay, we have the membranes. Today I'll show it in a couple of minutes, a couple of seconds. I'll show you the structure of the membrane, and it is done. And as you saw, it is done very, very efficiently. Okay, now what is reverse osmosis? Okay, in reverse osmosis, we take either seawater or brackish water. Okay, we have a selective semi-permeable membrane in the sense that these membranes can allow water to go through it, okay, and it rejects salt, organic components, and many other things that you can find in different types of water. Okay, so on the other side of the membrane, we get almost pure water. Okay, I'm saying almost because, as you can understand, there is no perfect membrane. Okay, absolutely not. Okay, there are different types of membranes. Each one has its property, the rate of rejection. Okay, but compared to the water that is taken as a feed, this can be considered as pure water, and water that you can consume safely. Right? Okay, what we are doing here, as you can see here, we apply pressure, okay, in order to push the water through the semi-permeable membrane. And let me ask you, can you guess what should be the minimum pressure in order to achieve this? Can you guess? We are talking about reverse osmosis. Okay? The key word here is, come on, you should know it. You know it. You know it, I'm pretty sure. What is the key word here? Have you heard about osmosis? Yes? You heard about it, no? Okay, so the minimum pressure that we have to apply in order to be able to push the water through the membrane is the osmotic pressure. The osmotic pressure of the feed. Okay? Do you agree with me? Otherwise, we have to, in other words, we have to overcome, okay, the osmotic pressure of the feed in order to be able to do this kind of separation. Okay? It just goes to say that we actually, not as we call this technology reverse osmosis. Osmosis is a natural process. Okay? We cannot reverse it. We can just overcome it. Okay? So in a way, this term reverse osmosis is misleading. Okay? But that's how we call it. Okay? So again, the minimum pressure that we should apply in order for this process to be achievable, okay, is the osmotic pressure. In seawater, it is around 35 bars. Okay. In brackish water, it depends, of course, on the salinity of the water. As the water is more saline, you'll have to apply higher pressure, okay? But the actual pressure that we apply here is twice the osmotic pressure. And that is why because while doing it with seawater, for instance, we double concentrate the seawater, which means if we start with 35 grams per liter, we end up here on this side with almost 70. Okay? With almost 70. And in fact, this is 70 bars, 60, 70 bars. This is the actual pressure that we apply in those installations of seawater desalination based on reverse osmosis. This is the kind of pressure that we use there. Okay, 60 to 70 bars, depending on the type of the membranes. So we have here the high pressure part of the plant. Okay, here on this side, and here we get the pure water. Now, as I mentioned before, if we do seawater desalination, dealing with the brine is not a problem. We just bring it back to the sea. Okay. But with brackish water, it is much more problematic, and we have to deal with it in a much clever way, and also costly. Okay, the technologies that we are using in order to deal with the brine are more costly in inland. Any questions about it? Is that clear? Everything is clear? Okay, good. Okay, okay. When you go into a desalination plant, RO desalination plant, that is what you see. Okay. Many of these pipes, or actually containers, okay, long containers, okay, that you see. And these containers, if you look closer, that is what you see. Okay, you see these are very robust containers. Okay, and the fact that they are robust is because, first of all, within these containers we put the membranes. I'll show it to you in a second. Okay, and as I said, we have high pressures. Okay, so they have to be stable under these pressures, and that is why they are very robust. And when we go further inside these containers, that is what you see. These are the membrane modules, okay, which look like this. And here you have the membrane here, and you have one spacer on this side, another spacer on this side, okay, and all these, all the three of them are up on themselves. We call this structure a spiral wound structure, okay. And why we do it why we are doing it like this? The reason is that we would like to have as much as surface area per volume, okay, in these kind of containers, okay, because you may understand that the production capacity of a plant depends on the surface area of the total surface area of the membranes that you will have in this plant, okay, right? So we need to have it as much as larger as possible within a certain volume. And also the other factor which is important is the footprint of the plant. Okay, usually, you know, land area is very expensive, so we would like to have the desalination plant as small as possible for its capacity, right? Okay, so this is the reason why we use this spiral wound structure for these kind of membranes. Now let's go further and take a look at the membrane. I promised to show you the structure of the membrane. So this is the structure of the membrane if you zoom it up, okay? And what you see here is what you see here are three layers. This is one of them, the second one, and the third one. The upper one is, in fact, the selective layer through which we push the water, and this is the layer which, in fact, is doing the job of separating from water. Okay? This layer is made with a specific kind of polyamide, and if you remember, polyamide, nylon, for instance, is a polyamide. Okay? But nylon is a linear polyamide, and what we have here is not a linear but aromatic polyamide, which has a special structure which allows us this job of separating water from salt. And as you can see here, okay, it is a very, very thin layer. Okay, it is depending on the type of the membrane, it is between 100 and 300 nanometers thick. Okay, the other layers are there just for supporting this very, very fine layer and delicate layer. Okay, so it will be kept, its integrity will be kept all over the way. Okay, for long time. And these are polymeric layers, okay, and they support it. If you want, it is not that clear, I guess. These are TEM image. This is a TEM image of this layer, and you can see here. This is actually the upper face of this layer, which means this face is this face here. This is a cross section, okay, of the layer. Okay, we call it, by the way, this kind of membrane, we call them TFC, thin film composite. Okay, because these are composite membranes. Any questions?
You're very shy. You're very shy today.
I'm pretty sure that all is clear to you. Okay. No, I cannot force you to ask your questions, you know. Right, okay, let me skip this. Okay, I want to go further. Yes, to wastewater treatment. Okay? As I mentioned before, it is wastewater becomes a very important water source in the world today, and in my country we recover more than 85% of our wastewater, municipal and industrial wastewater, and you can see it here. Okay, it shows you the percentage of wastewater that is recovered in Israel as compared to other countries in the world. Okay, and let me give you, and the total wastewater volume that is generated in Israel is almost 500 million cubic meter per year. Okay, and 85% out of that is being recovered. Okay, so you can get an idea on the amount of water that we can save while doing it. Okay? Yes?
What is the use of that treated wastewater? Is it irrigation? Is it consumption?
As I mentioned before, it is used today, most of the water, okay, that is covered. Of course, there are different levels, okay, of treating this water. I'll show in a couple of seconds. I'll show you how it is being done in our main plant of wastewater treatment in Israel, but most of the water goes for unlimited irrigation, okay? And actually today, this is the main source of irrigation for agriculture. Okay, this is also the main source of irrigation for gardening today in Israel. Right, in many municipalities, they use today treated wastewater for gardening. Okay, and I didn't mention it, but by law today, each municipality has to treat to some level or another its wastewater. Okay, this is by law. Every municipality has to do it. Okay, so this is the main water treatment plant that we have today in Israel. It is located not far from the Tel Aviv, and actually it collects the wastewater that is generated in what we call Tel Aviv Metropolitan, okay, which today, if I remember correctly, it has almost 3 million people. Tel Aviv Metropolitan, it is not just Tel Aviv, including some other cities around Tel Aviv, and it treats today actually more than 150 million cubic meters per year. Okay, all of this goes after treatment to unlimited to the agricultural farms. Okay, to the farms for unlimited irrigation. Most of the water goes to the southern part of Israel. Okay, and the treatment, as you can see here, this is an anaerobic, this is aerobic digestion, okay, activated sludge, what we call, and there are several stages. I will not go to all the details. We have here preliminary treatment, which actually in which the largest particulates are being separated. Then we have primary treatment, the secondary treatment, and the most important one is the tertiary treatment, which is typical to this plant. Why? Because this tertiary part, in this tertiary part, what they are doing there, they take the water after secondary treatment, okay, which is, I didn't mention it, but you have to understand that this is a biological treatment, actually, aerobic, okay, digestion. They take the water after filtration, they bring it to sand dunes, a large area of natural sand dunes that we have not far from this plant, and the water is introduced to the sand dunes, and it is getting infiltrated into the sand dunes. Okay, it stays there for around 400 days, more than a year. Okay, until it is being pumped again. Okay, in the soil, which is a huge, you can consider it as a huge filtration facility, if you want. Okay. We actually, most of all the viruses, all the bacteria, all the organic residues that are being there are trapped in the sand dunes there, okay? And the water that is pumped after 400 days is in a very good quality. Here you see the action, okay? What happens in these sand dunes, okay? This is the zone of its reduction, and it is getting it is getting infiltrated through the zone, and these are the pumping points. Okay,
Sorry?
here, yeah.
The storage is natural, or
Excuse me?
the storage is a natural.
Yeah, the dunes are natural. Yeah,
The place where the water is, it was also prepared, or maybe you open more space, or it's the natural place.
it's a natural place. But I can understand your question. Indeed, there's a problem there, you know, that these dunes, okay, dunes are soil actually, okay? Dunes are soil. These dunes are getting clogged while you're using them, okay? So they have to wash it. I don't know how often they are doing it, okay, but every once in a while, okay, they have to wash it. They have to aerate them, you know, again, okay, in order to be ready for the next period of usage, okay. So this is a very good point. Yeah. Okay, but I can tell you that I don't remember for how long this plant, okay, was first came first to operation. I think almost 20 or even 25 years ago. Okay, and since then it is under constant operation, you know, and they somehow they overcome this kind of problem. Okay, the fact is that water is being supplied constantly to the agriculture, and you can see here on this graph it shows you the total percentage of volume of water that is being used for different of different water types that are being consumed in Israel, and you can see here that the water for agriculture, okay, this is the water for agriculture, the agricultural sector that is being used in Israel for different water sources, okay, and you can see here that the potable water is declined throughout the years, and this is thanks, first of all, to the use of brackish water, and to the use of brackish water here, okay, and to the use of effluent, recovered effluents that we are using, okay, right? Good. I'll take a few minutes and I'll finish, okay? So this is again thanks to the recovery of wastewater that we have in Israel. Okay, I think that I finished your answer. Okay, right. Okay. So if you have any questions, first of all, thank you for being so patient, and yeah.
No. Thank you so much, Yoram, for your wonderful.
Thank you.